Good morning. The first work, it's by PACELLI ZITHA from Delft University. And the title of the work is Investigation of the Recovery of Medium Heavy Oil by Gas Injection. Please.
Okay. Thank you. First of all, I would like to thank the organizer for inviting me to this workshop. I would also like to, this was made possible also because of my presence at the Universidade de Fora. So I would like to thank Grigore Shapiro for making that possible. Now, this presentation will be a little bit different from what you have heard so far. The focus has been on let's say, mathematical modeling, analytical. I enjoyed it all the way. But trained as a physicist, I developed into, let's say, an experimentalist. I work very close to oil companies. So the concern about the, let's say, applications of what we are doing is maybe more dominant than you more privileged people who can devote more time to theoretical stuff. But anyway, I hope that we can find common ground over there. Now, before I go on, I just want to highlight the people in my group. They are most of them are working on CO2 related stuff. I mean, if you have questions about what you are doing, we can discuss that later on. My presentation is about CO2 injection into oil reservoirs to both recover oil and also as a means of storing the CO2, of capturing, of storing the CO2. So the structure of the presentation, I will have a short introduction and maybe discuss a little bit motivations and objectives, and then I will talk about experiments, and later on I will show you some results of experiment and discuss some conceptual ideas for modeling, and then I will give you some conclusions. Now, the motivation of this work came from my contacts with Statoil, which is the national oil company of Suriname. Suriname is this country here. As you can see, there is a huge border with Brazil, so you would think that it's not far away from here, but it's a huge country, in fact, at least compared to some European countries. And then they have three main oil fields, and this is the Tambarejo oil field, which has been producing for over 20 years now. We will see the data in a minute, and then the question that they had already in the years 2000 is that how can we maintain the production of this field? The field is under what we call primary recovery, which means that it uses the natural pressure present in the reservoir to produce the oil, and then when this pressure diminishes beyond a certain point, you have to now inject water or inject other stuff to make sure that the oil continues to be produced. Now, here are some details about the field. For those who are interested, it's a field that is fairly shallow, 900 to 400,000 feet. That's relevant for what we are going to do later on. And then it contains oil that is heavy, medium heavy oil, with the viscosity of 650 to 1,000 centipoise. So this would be like, I don't know, olive oil at 15 degrees Celsius or so, more or less. So much more viscous than the normal cooking oil. And then this is the porosity, the permeability. So these are real data, but you shouldn't attach a lot of significance to them because there can be variations. And the field is big, so the data can vary over the field. And as I mentioned to you, there were discussions in this company in 2013 that led to the start of a pilot project. They injected polymer, which started in 2008, and it's still ongoing. They're expanding. So basically, you dissolve a polymer into water in order to increase the viscosity of the polymer. And then by so doing, you make sure that the viscous fingering that was described in some of the presentation previously is diminished quite a lot. And then they did a second screening study in 2011, and the question came, should we use gas? And the screening study actually showed that gas would be a very good candidate for increasing oil recovery, even better than polymer, but more difficult to implement. Now, as I said previously, the reservoir is shallow, so pressure is low. And what we expect is that the displacement with the gas will be immiscible. And that it's really important. It's, I think, the basis of the questions, the scientific questions that we try to answer in the studies that we did afterwards. And then, now, the whole study to check whether we can apply this technology to the field involves a number of things. So first of all, what we call PVT study, so the study of the properties of the fluids together with the gases, and the thermodynamic properties, and then also very detailed reservoir simulations, which I'm not going to discuss here. Okay, what I want to discuss are what we call core flood experiments, as you have seen in the previous talks. These core flood experiments can be used to calibrate our models, to obtain data first, but also to calibrate our models. And once we are happy with the models, we can cast them into the reservoir simulations and then try to predict what happens on a reservoir scale. Now, so we did a set of core floods at what we call reservoir conditions, so at exactly the same pressure and temperature as in the reservoir. We tried also to mimic the injection velocities that you would find in the fields. And the basic conclusions from that is that if we use WAG, you get up to 66% of the oil initially in place. And then that if you inject CO2 only, compared to nitrogen, you will get 2 times more higher recovery. And we attributed this to the swelling of the oil, and then also to the reduction of viscosity. So if you dissolve the CO2 into the oil, you will reduce the viscosity. And then what was very interesting to observe is that both WAG for CO2 and nitrogen after a number of cycles resulted in more or less the same recovery. So there were a lot of questions, how is that possible? In fact, for several months we have been dealing with this question. We didn't quite understand why this could be. Now, so I decided to take this problem and then to bring it to one of the PhD projects that I had in Delft. But this project was related to CO2 storage. And then I will pass very quickly through this image. I think that everybody here must know more or less about it. Now here we have, so it's a huge project with almost all university in Holland, where we investigate the whole chain, capture of CO2, transport, and then storage in geological settings. This is storage in deep aquifers. So we have been doing quite a lot of work on the injectivity. But what is relevant for us here is really try to combine CO2 EOR and the storage of CO2. And this picture maybe illustrates what the idea would be. So here we have, let's say, a power plant. It could be also a cement factory for the same matter. And then we want to store the CO2 here. Now, what will happen after a certain time is that the CO2 will be produced together with oil and brine, and then there will be a whole machinery, a whole factory to separate out the different fluids. Now, oil will go into the market, and then we will recycle the CO2. Now, if we do this for sufficiently long time, we call this a washing machine type of process, but with CO2, we will have the oil that will continue to be produced, and at some point we will have stored enough CO2 into the underground. And then the questions that we had is now how to enhance oil recovery while at the same time sequester CO2. Maybe I should say, is that possible? Okay, this seems to be a little bit contradicting effect. And then how the pressure, the pressure that you have in the reservoir will influence both the recovery and CO2 storage. This is just a picture to show. Now here you have the cap rock, the porous medium, and then the CO2 that at some point will be trapped. In fact, in almost all reservoirs, you will have the oil on top here, and then underneath here you will have water. And then the idea is that you can store the CO2 into the water layer, and then some of the CO2 will be used to recover the oil. But let's focus a little bit on CO2 EOR. I mentioned to you already in relation to the oil field that now if you have a shallow reservoir, basically you don't have the miscibility, which has been the basis for all CO2, for the success of CO2 projects in the United States of America. So it's not really a new technology. It has been applied extensively in the United States, but in many cases in the United States you are dealing with light oil, and then you create a zone where the oil is miscible with the CO2, and then what happens is that if you have this is the injected CO2, and then here you have oil. These oil blobs will swell, and then they connect, and you can displace them quite easily from the reservoir. And also, the viscosity of the mixture of CO2 and the oil will decrease. And there are several ways to do this. You can do what we call continuous injection, which, like in the previous picture, you have here an injection well, and then you are producing the fluids on the other well. And that will be really let's say, the mental picture that will serve as a basis for our experiments. Another way of doing this is to do what we call cyclic CO2 injection. There is a similar picture for steam injection. And then it was discussed in the previous talk this morning. You can also use what we call water alternating gas. Now, if you inject CO2 in porous media, I think yesterday this was also touched upon. You can have different mechanisms of trapping. You can have structural trapping, residual trapping, which means that you create a residual CO2 amount. You can also have the dissolution of the CO2 into the water, and then you can have mineralization, which is chemical reactions that will create solids that will remain trapped into the porous media. And here you have how the different mechanisms operate over time. And for us, we were thinking more into this, the initial stages of the injection of the CO2. And you see here the different mechanisms. Here you see the fingering of the CO2 over long times. And then we define here what is storage efficiency, which is the mass of CO2 divided by the pore volumes. Now, what I want to explain to you are the experiments that we have done. So this is the setup that we use. So basically, we have a sandstone core, so a real sandstone. We call this an outcrop. So it's a sandstone which is extracted from geological layers that emerge somewhere. Well, in this particular case, in Germany, this is a Bentheimer sandstone. You have a system here to inject the fluids, and then you have a system to regulate the outlet pressure. This back pressure was important because it was one of the parameters that we wanted to investigate. And we designed a special system to be able to collect and quantify the different fluids produced. And this is how the setup looks like. Now you have here the computer for data acquisition. There's a data acquisition system. And then you have another laptop here for controlling some of the device. The pump is a pump. And the core holder is over here in the CT scanner. Quizix pump for the liquids. And the clock, which is used to measure the gas. And this is how we place the core. It is centered here in the middle of the gantry, vertically, in such a way that we can obtain cross sections, and then we can move it. We obtain cross sections at different locations in the core, avoiding the middle because we have metal parts which are not so friendly to the scanning, to the X-rays. And these are some of the characteristics. Now here you have the different pressures that we tested, and here you have the density of the CO2 and the viscosity of the CO2 and also of the other fluids. Obviously, for water and oil, there is no change. Instead of using the crude oil from the field, we used a pure hydrocarbon because this was for research purposes. And then this is how we process the images. Here you have the CT scan, which is just a matrix that we can code with color to see which fluids we have. This is a dry core. And then we convert that to attenuation coefficient. And by making difference, we can have the saturations of the different fluids inside the core. This is a typical sequence of an experiment. We first saturate the core with brine, then we do a primary drainage, and we simulate water flooding. And after water flooding, we inject CO2, varying the pressure. Now, this is a typical image that we obtain for the injection of brine. We inject it under gravity-stable conditions, of course, and we have to inject a fairly long time in order to obtain uniform saturation. Now, after we have done that, we measure the permeability using Darcy's law. And after measuring the permeability, we do a primary drainage. Now, these graphs, they are here just to show you that for the different pressures that we use, we obtain the same result, which is not surprising. And there are small differences, which are due to the fact that the cores that we use, for every experiment, we use a different core, and they have properties that are slightly different. Here you can see the breakthrough time, and this is how you have oil and water saturation in the core, how it varies as a function of number of pore volumes injected during primary drainage. And here you can see how the oil is displacing the brine in porous media. Now this is these are the CT scans, so the saturation profiles that obtained. Don't look at the lines; they should actually not be there. They were connected. They connected the points in a way that is not so interesting. But you can see a very nice front-like displacement, which comes from the fact that the oil is more viscous than the water initially present. The viscosity of, as you saw in the table, of N-hexadecane is about 3 compared to water, so 3 times that of water. Okay, and here you see the cumulative production of for this primary drainage, and it is a nice. This is nicely in agreement with the predictions of Buckler-Leverett flow for Buckler-Leverett theory for two-phase flow. And then what we do next is to do a water flooding, and you see that the pressure drop starts to behave a little bit different here, but the main part of the pressure drop is here, where you see a nice decrease after water breakthrough. Here is the point where water breakthrough. Also, the breakthrough time that we obtain here can be derived quite well from the Buckler-Leverett theory. These are the corresponding variation of the oil and water saturation, and you see here, of course, that the oil saturation will decrease. Well, in these two experiments to about 40%. Here to a slightly lower value. Again, the samples are real samples. The porosity and the permeability are not exactly the same, so there is always a bit of variation in the results that we obtain. So these are the residual oil saturations that we obtained for the different pressures, but it's not really related to the pressure in this case. It's just the difference in the properties of the sample. And this is the displacement of the brine. So these are the corresponding saturation profiles. This indicates the direction of flow. And also here we see that we have a typical behavior of the breakthrough curves that is predicted by Buckler-Leverett. Here we have the cumulative recovery, which was obtained from both the effluent, so by measuring at the outlet of the core, and here from the CT scans. We wanted to check that there was not anything crazy happening, that we got the same results, and now quite happily we noted that both CT scans and effluents give very close values within experimental error that is acceptable. Now this is the pressure drop during CO2 flooding. We see now a lot of fluctuations. These fluctuations are not always physical. They're created because we have a back pressure in order to control the pressure at the outlet. And then, so the opening and the closing of the back pressure depends really on the injected pressure. It's something that we need to improve. But anyway, here we see the different breakthrough times for the CO2, which is way above 1 per volume. Okay, so that's a little bit strange. How is this possible? The only way you can have CO2 being delayed so much is because you are dissolving the CO2 into the water in the system. And these are the images, and you don't see much here. The reason being that, the CO2, what the CT scanner measures are densities, okay? And then if you dissolve CO2 into brine or into oil, you increase the densities of these fluids. Only after a long time, when the saturation change dominate, you will see a change in the flooding. But we could, extract from these data how the saturation of the different phases are changing. So here you have the water saturation that obviously is decreasing, and also the oil saturation. They're both decreasing to a certain value here, and you see that the gas saturation is increasing, the way it should be. And you see here the cumulative water as a function of number of pore volumes injected. Now the water will jump very quickly to a constant value here, while the gas will continue to increase for a long time. And oil production will start more or less here together with the breakthrough of the gas, and then will stabilize at some value. You have to read the cumulative amount of gas produced on this side. Now, one thing that we noticed in many of these experiments is that the pressure drop will, as I showed before, there are a lot of fluctuation, but you can see that the pressure drop increases and drops, which suggested to us that there was a kind of foaming, and there was something going on that increases the viscosity. So we decided to see whether there was a foaming taking place. And I have here just a movie to illustrate what happens when you have foaming. In this particular case, we don't have oil in the system, but I thought it would be useful to show that. So what you see in red is the core saturated with brine containing a surfactant, and then we are injecting gas into the core. And what you see is that you have a nice frontal-like displacement taking place in the core. And over time, you see that the gas saturation is increasing a lot and a lot. I don't know, maybe it went a bit fast, so I will run it once again. This is a horrible thing. Okay. Now, these are the cumulative production of CO2. Am I doing it? Of CO2, and where we clearly see here, first of all, the water flooding, and then the incremental recovery from the effluents and the CT scans due to the injection of CO2. I think this thing is a little bit just... Sorry about that. I need to put it somewhere else. Yeah. So sensitive. Okay. Now, the results are summarized here, and so here, I'm just going to look into the results for the CT scans. You have water flooding. So on the average 40 to 59, this is maybe an outlier. And then you have for CO2 flooding, you have an incremental recovery. And the point that is important to note here is that as we increase the pressure of the CO2, the incremental recovery by CO2 will also increase. And then now here you have the total recovery, which is obviously the sum of the two. Now, so we came to a point here where we asked ourselves, but how is it possible that that just the injection of CO2 under immiscible conditions can lead to can lead to incremental recovery. Actually, the experiments that I didn't show here, which we did with nitrogen, which gave the same result. I mentioned that in the first slides. So we decided to look at, to replay, in fact, the experiment in this three-phase diagram. I realized that I used a completely different notation than it was used this morning, but that's okay. So to be clear, SO means that the notation I'm using means that the saturation, the oil saturation, is 1 over here. Water saturation is 1 over here. And so our experiment actually starts here with the core fully saturated with brine. And then we are going to do our primary drainage towards connate water saturation. And we did, and after we do a water flooding, okay? And then after doing this water flooding, we do gas flooding, basically. Gas flooding with some foaming and etc. But basically it's a three-phase flow. So this change from two-phase flow to three-phase flow is actually responsible for us recovering more oil. I think you can just read the oil saturation. So this difference here between the residual oil that you have there and the residual oil that you had for water flooding is in fact what is responsible. So what it means is that whatever way we do this, in the end we should end up, so if we increase gas saturation sufficiently, we should decrease our oil saturation to the value corresponding to this point here. And then one thing that we can observe already is that if we start at a higher residual oil saturation for water flooding, of course the gain that we will obtain with gas flooding will also be less. And then, okay, so we want to compare nitrogen and CO2, and in this specific case, what we are going to do is to do an experiment where we first inject the gas and then we inject the water. Now that means we start here at the connate water saturation, and then we inject, in this particular case, nitrogen, and in this case we inject CO2. In both cases, it is immiscible. I should go to the conclusions. That's the idea when you stand up. Yeah. Okay. And after we move here by injecting water to a lower oil saturation. Okay. And then we can apply the same principles to work. And okay, I will skip the whole story about CO2 storage. I think you will get the presentation. So if you have questions, you can contact me. And I will move to the conclusions. And the basic idea is that now, by using CO2, I will let you read the conclusion. So the basic idea is that we can, well, at least the experiment suggests that we can, at the same time, increase oil recovery by injecting CO2, and we will trap part of the CO2 in the core. Under immiscible conditions, we can explain why the incremental recovery takes place by using the three-phase diagram. And then I think that these are now, at least, that we have laid the basis here for further investigation into the effects of gas injection, which can be applied for WAG or for continuous gas injection. Thank you.
Thank you, PACELLI, for the nice talk. And we have time for one